All right, so I think we're gonna start. Um, these are the notes that I posted on the classroom earlier today. I think maybe yesterday. I think it was today. Um, so yeah, if you do want to look at it just on your own, that's where you'd find it. So anyway, today's topic is going to be polynomials and factoring. So we're moving away from geometry and going into algebra. And I think this is one of my favorite topics because there really aren't too many things to, or there aren't really too many theorems or concepts to really understand. A lot of it is just applying basic ideas into harder problems, basically. All right, so first I'll define what a polynomial is. I wrote it in sigma notation here, where it's just the sum from k equals 0 to n of a sub k times x to the k, where your variable is x, and the a sub k is just any coefficient, and meaning that it's a constant, and the k is an exponent. So this is really just a condensed way of just saying like any expression with like some sum of powers of x, and that's really it. So this is just a random polynomial that I wrote x cubed plus 2x squared plus x minus 1. So yeah, in general, any polynomial can be written as in this form, and this is kind of like a like a more formal way to write it. Most of the time, you won't really see it. It's just going to be written as just some sum of powers of x. All right. All right. So if you don't understand what the symbol it means, that's totally fine actually. But basically, you'll see that I wrote these two symbols here and here. They're called sigma and pi, or product notation. And basically this backward E symbol, you could call it. This is an uppercase sigma, or the Greek letter, and the uppercase version. So basically this means sum, and it usually has some kind of index. So you usually see some variable k equals to 0 and n here. This basically means that as your integer k varies from 0 to n, and you have an expression. So for example, I'll just do sigma like this. This just means the sum of all k from 0 to n. So this is equal to 0 plus 1 plus 2 plus all the way to n, where basically what the sigma does is it takes k equals 0, plugs into this expression and gets 0, since the expression just returns k. And then after 0, you go to k equals to 1, and then that's equal to 1. So you plus 1 here. Then you go to k equals to 2, and that returns 2. So you add 2, and so on. So k just keeps on increasing by 1 until you get to n, which is this final index. And then that's just here, this last plus n. And then you just add them all up, as that's what the sigma means. And basically this product notation, it's the same thing except for you're multiplying everything together. So I'll just take the example that I wrote for polynomials, where any polynomial can be factored as this product of x minus r1, or not r1, r sub I, where those are the roots. And basically this expression just simply means if there are n roots, this is equal to x minus r1 times x minus r2 times x minus r3, and so on, to get to x minus r sub n. So this is really all that this notation means. And I do have to have an equal 0 here. So basically in most instances, you'll see polynomials. They're going to ask about the roots of the polynomial. And the root of a polynomial is the value of x that would make the expression equal to 0. So, for example, if your expression or polynomial is x squared plus 2x plus 1, then your root is just going to be equal to -1, because this expression is equal to 0 when x equals to -1. And it also happens that -1 is the only value of x that makes it equal to 0. So that's what the root of a polynomial will be like referred to as. And you can also like see, or not see, but like sometimes you'll see that is referred to as like a solution of the polynomial, and that just means the same thing as the root. So just that's kind of a key term to know if you aren't familiar with it already. Yeah, so the most important, or two most important formulas for polynomials are the Vietnamese formulas, and the quadratic formula. So most likely you'll have learned the quadratic formula in school. So you should already be quite familiar with it. But the Vietnamese formulas basically is a great way to solve these types of AMC problems where your roots and your coefficients, where you're only going to be given like one part of that, like the information that you can get from a polynomial. So like a lot of times you'll like only have just what the equation of the polynomial is, and you have to find some property of the roots or the other way around. So that's why Vietnamese formulas make it easy to relate the coefficients of a polynomial to its roots, so that it's easier to tell in some cases. Well, you'll see. So basically, for a quadratic equation, which is the most common type of polynomial that you see, and it just means that the degree is 2, or the highest exponent of x is 2. We have that negative b over a is equal to r1 plus r2, where the roots are r1 and r2, and c over a is equal to r1 times r2. And the reason why this is true is because if we take the quadratic, since it's ax squared plus bx plus c, we know that it can be factored into a times x plus r1 times, or not x plus, x minus r1 times x minus r2 is equal to 0. And I did forget to mention here in the product notation that you do have to have a leading coefficient outside of everything as well. Since this a here, like if you just divide it out, you'll be left with something like x squared plus b over ax plus c over a is equal to 0. And since we know that this right side is equal to 0 if we're finding the roots, it doesn't actually matter if the a is there or not. So that's actually what we do in this case. You just divide this a out, so it just disappears basically, and we're left with this next equation. And basically, if we FOIL out, and FOIL just means like multiplying and expanding out these two binomials, this is equal to x squared minus r1x minus r2x plus r1, r2. And these two quadratic equations have to be the same. And that means that the coefficients must be equal. So if we take the coefficient of x on the right-hand side, this is equal to r1 plus r2, or the negative of r1 plus r2. And this must be equal to the coefficient of x on the other side, which is b over a. So you can immediately get that r1 plus r2 is equal to negative b over a. And similarly, r1 plus r2 is a constant term on the right side, and c over a is a constant term on the left side, so they must be equal. And this is why the second part of the formula is true. All right, so various formulas really just are derived from expanding the polynomial as a form of the product of x minus its roots. And so that's how we get there. And once you like know or memorize, most likely, you'll see that this comes in handy very often. And I do want to just skip quadratic formula for now and go to cubics. And basically, the Vietnamese formulas works for cubic equations as well. So you can see the three equations here. Negative b over a is r1 plus r2 plus r3, where those are the three roots of the cubic. Since like this degree of x here is 3, we know that there are going to be 3 roots at most, since this can be written as like a product of like degree 1 polynomials, and you can only have at most 3 of these x minus r's, because if you had more of them, then the highest degree would be more than 3, since there would be 4 x's. It would be x to the fourth. There would be an x to the fourth term if we had another root. So that's why like the maximum root here is going to be, or the maximum number of roots is going to be 3. So with that established, then we can kind of do the same thing. So the way that you derive vietas for quadratics is the exact same for cubics. You simply just expand it out. So the end results are just here, where negative b over a is the sum, negative d over a is going to be the product, and c over a is going to be the sum of just pairwise products. And this vietas can be generalized to higher degrees. So I wrote it down up here. The first coefficient after the leading coefficient. So the coefficient of x to the n minus 1, if the polynomial has degree n, that's equal to, that's going to be corresponding to the sum. So negative b over a is always going to be the sum of all the roots, no matter how many roots there are. And the last term is going to be corresponding to the product. And by last term, I mean the constant term, so the x to the 0 term. So just any value like here that does not have x attached to it. And then everything in the middle is just going to be the product of some number of the roots. And so like, how should I do this? I wrote it here. In general, for a degree n polynomial, the coefficient of the term with degree n minus k is the sum of all the products of k of the roots. So for example, in the cubic, we would have this, right? So if we had a quartic, which is power 4, then we know that negative b over a is equal to r1 plus r2 plus r3 plus r4. And c over a is going to be equal to r1, r2 plus r1, r3, and plus all the pairwise products. Then negative d over a, I'm missing a constant term here. Negative d over a is going to be equal to like the product of 3 of them. So we just have like every possible product of 3 roots, and then p over a is equal to the product of all of them. So each one kind of increases by 1 of how many product of roots you're adding, if that makes sense. And the last thing to note is that these alternate signs. So the first sum of the roots is always going to be negative b over a. So this is like your starting point. It's always going to be negative. And then afterward, it just alternates between positive and negative as you go down. So that's why for a quadratic, we have a negative positive here. Then cubic, it goes negative, positive, and negative. So that would be how you could tell whether everything has to be negated or not when you're solving. All right, so does anyone have any questions on Vieta's formula? All right. Well, I do want to mention that it's mostly like, it's not like technically a formula. It's really just an easy way to like remember how the roots are related to the coefficients. All right. And the last thing, or the last formula regarding polynomial we're going to talk about is quadratic formula. And I'm sure most of you are familiar with it. If any of you are not familiar with it, this basically just gives the roots of a polynomial with equation ax squared plus bx plus c equals 0. So here, a, b, c are the coefficients, and this is the formula. And the way that you would actually show that this is true, so the way to derive this formula is by something called completing the square. And what completing the square means is, I'll show you. If you take the first two terms, ax squared plus bx, right? We want to make this a square term. So what we can do is, for one, I probably should have done that first, actually. We want to take away the leading coefficient because it's going to be kind of annoying to deal with because we don't know if it's going to be squareable or not, or perfect square or not. Right, so we can first go from this equation to this equation. You just factor in an a, and this time we're not going to divide out the a just yet. We just want to create an equation of the form like so. And the main idea with completing the square in a quadratic equation is that any like perfect square polynomial, quadratic, I mean, must be in the form x squared plus 2rx plus r squared. This is kind of just the expansion of the square of the x minus an r. Right? And we can kind of do the same thing with just any general ax squared plus bx plus c polynomial. So if we can like add a value that would work here, which would be b squared over 4a. I want to say b squared over 4a squared here, plus c over a, then minus b squared over 4a squared. And since we're adding a b squared and 4a squared, and we're also subtracting it, it just, the thing just, like, it's like same thing as adding 0, since you're adding both the positive and negative version of that number, you're not changing anything. So this is allowed. And then we can simplify this. So now that it's in the form of a perfect square polynomial, we can change x squared plus b over ax plus b squared over 4a squared into simply x plus b over 2a squared. And then we still have a c over a and a negative b squared over 4a squared left. So we'll just like just distribute it out of the parentheses, and we're just left with this. All right. So now afterward, now we just have to isolate the x and the b over 2a. Like this. And then I think it's pretty clear how it's completed after this. You just divide by a here. So you're going to be left with something like this. I'm sure you can follow here. This is just c is equal to 4a times c over 4a. So I just consolidated that into one fraction and then divide by a. So now we can take the square root of both sides. So you get x plus b over 2a is equal to the square root of b squared minus 4ac all over the square root of 4a squared, which is just 2a, right? And then since we know that the square root of a number can technically be both positive or negative, since a square of a negative number is still positive, there's a plus or minus here. This is where we get the two roots from. And then afterwards, you can just subtract the b over 2a to the other side. So you get x equals to negative b plus or minus the square root of b squared minus 4ac over 2a. So that would be how this formula is derived. I know that it's a lot of times it's not actually taught how to draw the formula, and you're just given it as like a true statement. So hope this this kind of makes it clear where it comes from. So I guess there's no confusion about that. All right. Is that good with everyone? All right then. I think go on to factorization part, and this is kind of a very specific factorizations. You won't see these too often, but when you do, it's really important to recognize it. And the first one is called Simon's favorite factoring trick. I don't know who Simon is. It's just what it's called. And basically just says xy plus ax plus by plus ab equals x plus b over x plus a over y plus times y plus a. And this is kind of probably confusing since I'm only using variables. So a lot of times in problems, you'll see something like xy plus, let's say, 2x plus 3y, and this is equal to 0 or something. And you want to find x and y. And I will make a note that this is only really useful when you're given in the problem that x and y are integers. So just note that if you are given that, this is where you would apply it. So if you have this, then the main way you could use Simon's favorite factoring trick here is by adding 6 to both sides. And the reason why you do that is because this coefficient 2 and coefficient 3, their product is equal to 6. And if you add that, then you're just adding this AB term here. So when you add 6 to both sides, you get this. And then now this just factors into x plus 3 times y plus 2 equals to 6. And the great part about this is that in problems where you're given that they're integers, you can simply just factor 6. So 1, 6, 2, 3, 3, 2, and 6, 1, and maybe like -1, -6, -2, -3, -3, -2, and -1, -6. Basically, these are all possible pairs of two numbers that multiply to 6. Then from there, you can just plug each of these values in for the value of the entire expression. And from there, you can find the value of just your x and y. So while you won't see this too often, a lot of problems will utilize it. So I think the most common one is actually when you see the sum of two reciprocals is equal to some number. I'm not too sure what number she used, but let's just say we know that this is equal to 1/6 or something. This is actually a pretty common problem. So if we're given two integers m and n such that 1 over m plus 1 over n equals 1/6, find all possible ordered pairs m and n. The way you would do this is by first consolidating the left side into one fraction, and then you can multiply it out as just this. And then when you subtract, you'll be left with an expression very similar to this one up here. And you can add like 36 to both sides and factor. And then from here, you can just simply factor out all possible, then you can just simply factor out all possible values that would work. and that would be it. So does everyone kind of see how this is useful? If you don't, that's fine too. But I just gave an example of a problem you might use it in. So next we have derivatives of squares, and this one is pretty simple. It just says x squared minus y squared can be factored into x plus y times x minus y. And this is easily shown by just expanding out the right side. So I won't do that. Just know that's true. And lastly, we have the sum of cubes and derivatives of cubes. So this just says x cubed plus y cubed and x cubed minus y cubed can be factored like so. And here you'll notice that this sign is a minus plus instead of plus minus, and that's on purpose. It just means that when this first one is a plus, the second one's a minus. And when the first one's a minus, the second one's a plus. So again, this can be verified by just expanding. So I won't do that here. Just know that it's true. And here are some tips. So oftentimes you'll see problems when they define a function as a polynomial. So like let f of x equals to something, and you're asked to find some f of some number. So f of 0 refers to a constant term, and f of 1 refers to sum of the coefficients. So maybe if you're asked to find the sum of coefficients, you'll know that you're actually asked to find f of 1, and vice versa. So these are true because if you plug in 0, all the x terms cancel out, and you're only left with the constant term. And when you plug in 1, again, the x's kind of become redundant, and you're just left with coefficients. And another tip is when you have like a cubic or higher degree polynomial that you have to factor or try to find solutions to, just simply try out small values of numbers, like 0, 1, -1, 2, -2, etc., and just see if there are roots. Sometimes there will be, sometimes there won't. It doesn't really hurt to try. And if you do actually happen to find one, then you can like use division and like divide x minus that root to simplify your polynomial. Next, I want to talk about the discriminant. And basically the discriminant of a quadratic polynomial refers to the part under the square root in the formula. So b squared minus 4ac. And basically if b squared minus 4ac equals to 0, that means there's only going to be one root. If it's greater than 0, then there's going to be 2 real roots. And if it's less than 0, then there's going to be no real roots. And that's true because if it's 0, then this plus or minus part is just a plus or minus 0, meaning that it's going to be the same either way. So it's just going to be negative b over 2a. And then if it's greater than 0, then it's just a plus or minus some number. So it's going to be two different numbers. And if it's less than 0, then you're taking a square root of a negative number, and that's going to be an imaginary number, which is not real. So that's how you would say the number of roots is related to the discriminant of the quadratic formula. And again, Vietas is very commonly used, so just remember it. And lastly, if a polynomial divides another, all of its roots must be roots of the other polynomial. And all this is really saying is that if a polynomial can divide the other polynomial, then since they can all be split up into like x minus its roots, the product of that, then there must be overlap between both polynomials. And again, all polynomials have the same number of roots as its degree. So that's only if you include duplicates. So while x squared plus 2x plus 1 only has one root, which is -1, it's a double root, meaning that both of its roots are -1. So because you're multiplying the same thing, x plus 1 twice. So while it like only has one root, it still technically does have the same number of roots as its degree. And lastly, if you ever see the term monic, it just means that the leading coefficient, which is a in most cases, is equal to 1. So anything that starts with x squared, x cubed, and so on, with this nothing in front is monic. All right, so that's really it for the formula or the lecture part, I guess you could say. So I think now we can go on to the problems. And so notice, I think I have, okay, like 7 problems plus challenge problem. So anyway, so the first one says the quadratic equation x squared plus mx plus n equals 0 has roots that are twice those of x squared plus px plus n equals 0. So what is the value of n over p if no coefficient is equal to 0? So again, here you're given information about the coefficients and about the roots. So it's kind of important to be able to tie those two together. And so this is where you would use Vieta's formulas. So first off, note that the only thing really connecting the two here in terms of coefficients is that m is in both of the equations. So first of all, we can write the Vieta's formula. So we have negative m is equal to the sum of the roots of the first one. So I'll just let the roots of x squared plus px plus m be r1 and r2, and the roots of x squared plus mx plus n equals to 2 times r1 and 2 times r2. And this is just a constraint from the problem. So since negative m is going to be like negative b over a, where a is 1, this is equal to 2r1 plus 2r2. And we know that m is also going to be the product of r1 times r2. So we basically have r1 times r2 is equal to negative 2 times r1 minus 2 times r2 from just our constraint on m. And next, we want to see what we're asking for, which is n over p. So how does this n over p fraction relate to our roots? So from Vieta's again, if n equals to 4r1 times r2, and this is from just the product of the roots, and the roots are twice of r1 and twice of r2. So the next p is going to be equal to r1 plus negative p at least. So p is equal to negative r1 plus r2. So n over p is just going to be equal to negative of 4r1 r2 over r1 plus r2. And from the first equation, we also have that r1 times r2 over negative 2, I guess, over negative 2 times r1 plus r2 is equal to 1. So I think you can see that these two equations are very closely related to each other, and that if you multiply by 8 on both sides, you'll just get this equation. And that's really it. So I guess the main thing to note is that you can like solve these problems for the most part without actually finding the values of the roots. You just need to know how to express the variables in terms of the roots and just like know what you're being asked for. So I think this is a great example of just how you can solve these problems using Vieta's formulas, and just knowing that, again, you don't need to know the actual values of the roots to be able to solve these problems. All right. So the next question, again, is a great example of Vieta's formulas. So it says, let a and b be the roots of x squared minus mx plus 2, and a plus 1 over b and b plus 1 over a as the roots of x squared minus px plus q, and ask for q. So the main thing to know here is that one possible way to do this problem is to try to somehow solve for the roots, because you only have like you can like kind of find the roots in terms of m here, but that's not really very helpful. as in it's not going to be very easy to find the actual values of A and B and just with what we know. But we do know that we're asked for Q, and Q is going to be equal to the product of the roots. So that is going to be like our lead. We know that A plus 1 over B times B plus 1 over A is equal to Q. And this is what we want to find. So we can just expand out this left side and see what we get. And if you do expand, this equal to AB plus 1 plus 1 plus 1 over AB. And you can just use, since A times B is AB, A times 1 over A is just 1. 1 over B times B is just 1. 1 over B times 1 over A is 1 over AB. And super conveniently, we know from the first equation that A times B equals to 2 because of Vietnamese formulas. So we can just simply plug in 2 here and get the answer. This is equal to 7 over 2. Actually, it's not 7, it's 9 over 2. Yeah. Or you can just say 4.5. So yeah, either way, again, this is just a quite simple application of Vietnamese formulas. So yeah. All right, next we have something a little bit different. So a polynomial x cubed minus ax squared plus bx minus 2010 has 3 positive integer roots. So what is the smallest possible value of a? Here we have to like take just see what we're given and what we have to work with. So we know this has 3 positive integer roots. And next, from Vietnamese formulas, we know that the product of these roots, so if we let them equal to x, y, and z, is equal to 2010. And we know that from Vietnamese formula again. Right? And we also know that the sum of the roots, x plus y plus z, is equal to a. And so we're asked what the smallest possible value of a is. And again, here the integer clause is what's super important. So we know that since x times y times z are integers, and their product of 2010, we can factor 2010, and this is how you factor it. 2 times 3 times 5 times 67 is equal to x times y times z. So basically, we just want to find 3 numbers that's like whose product is equal to this and has a minimum sum. And clearly 67 should be one of the numbers because if we do 67 times any other number, it's going to be kind of big, and it would be a lot smaller if we just had 67 on its own. So that's why 67 has to be one of the numbers. So next we're left with 2 times 3 times 5, and this is equal to 30. And we want to split 30 into 2 different numbers so that the sum of the 2 numbers is the smallest. And you can do this by trial and error. The smallest sum will just be from when you have 5 and 6. As 5 times 6 is 30, their sum is 11. Something like 3 times 10, the sum is 13. 2 times 15, sum is 17, and so on. So 5 times 6 is verifiably the smallest possible sum. So 2 numbers, 67, 5, and 6 will be your answer. So when asked for the smallest possible value of a, you just want the sum of all of these, which is just 78. So yeah, really what this problem is, it's like a polynomial. It's just a way to like disguise just this kind of number theory-ish problem as a polynomial problem. So as you like dissect the problem, you can see that it's not actually like super related to polynomials. It's just as long as you, again, understand the relationship between the roots and the coefficients, then you can kind of just change the problem into something that makes more sense. All right, so again, that's kind of the point of this problem. It's really, you'll see a lot of these problems. They simply just test to see if you understand what Vietnamese formulas are. So that's why they're important to know. Okay. Next we have, this actually has a pretty cool concept I do want to show. So this next problem says real numbers A, B, and C. They form an arithmetic sequence with A greater than equal to B, greater than equal to C, greater than equal to 0. And we'll talk about these sequences later in a later class. But what you need to know is that in a sequence, a CBA, I guess, that's what you're given. And by arithmetic, it just means the difference between consecutive terms is the same. So this just means B minus C equals to A minus B. Or as you'll more often see it, B equals to A plus C over 2. So that's really all that this arithmetic sequence information tells you. And then from here, it says quadratic ax squared plus bx plus c has exactly one root. Now this goes back to what I was talking about with the discriminant. All that this means is that b squared minus 4ac is equal to 0. And again, it's because this makes the part, like the square root part 0, which means the plus or minus is going to be plus or minus 0, which just means that both the plus and minus will result in the same number. So yeah, so we also have this. So we basically have these two pieces of information just from the problem given, and we're asked for the root. And the root of this problem is going to be negative b over 2a. And this is from the quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2. Oh. And we know that the discriminant is 0 here. So this entire right side can just be ignored, and you're left with negative b over 2a. So that would kind of be where you would get the what is this root part. So in essence, you're asked to find negative b over 2a. And when you're asked to find a relationship between these two variables, and you're really not given enough information to actually solve for any individual variable, where you only know the relationship between two variables, you have to find some way to substitute and simplify your problems. So try to eliminate a variable and just make it an equation within two variables. So what I chose to do is to change this negative b over 2a, the solution, by plugging in a plus c over 2 equals to b here. We can just have this as negative a plus c over 2 over 2a. These are the same thing since b equals a plus c over 2. So we know that we're really just trying to find negative a plus c over 4a. Right? And the cool thing about that is that we can split this into two fractions, negative a over 4a and minus c over 4a. And this just becomes negative 1/4. Okay, so this is just negative 1/4 minus c over 4a. And I guess the key observation here is that the only thing you really have to find is c over a. And this is because everything else is just some number times c over a. This is just 1/4 times c over a. So from what we have, we just want to find c over a. Then after that, we can plug into this expression and solve the problem. So this first part was simply just I guess you say the planning step. So once you have a clear goal in mind of what you're trying to solve for, then you can actually try to solve it. And since we're only working with C and A here, we can substitute B in the equation so we can get rid of it. So when we substitute B equals A plus C over 2 into B squared minus 4AC equals 0, you can get A plus C over 2 squared minus 4AC equals 0. And this is just substitution. So then after expanding, which is A squared plus 2AC plus C squared over 4 minus 4AC equals 0, you can multiply everything by 4 to get rid of fraction, which makes everything easy to work with. A squared, this 4 times negative 4ac becomes negative 16 ac, and 2 minus 16 is negative 14. So this is negative 14 ac plus t squared equals to 0, right? And here I like to think of this as a really common trick, is that when you have some equation in this form and you only want the ratio of the variables, what you can do is divide both sides by a squared. And the reason you can do this is since what happens is you'll get something like this: c squared over a squared minus 14 times c over a plus 1 equals to 0. So if you'll notice, this a and the a squared cancel out to become 1 over a here. So now the cool part is that this is just a quadratic with c over a as its variable. So you can just use the quadratic formula here, like so. I just want everyone to be able to see that this quadratic formula works with ratios of variables too. So if you let the ratio variable just equal to like a variable on its own, then you can like make it a quadratic, which you can solve it. So that's exactly what happens here. And basically this simplifies to, this should be positive here. It simplifies to 7 plus or minus 4 square root 3. And now we can go back to this requirement here. It says that a is greater than or equal to b, greater than or equal to c. So what that means is that c has to be less than a, which means that c over a has to be less than 1. So that means that c over a has to be equal to 7 minus 4 square root 3. And it's pretty easy to see that this is between 0 and 1, so it works. Then after that, it just simply becomes negative 1/4 minus 1/4 times c over a. So like this. And this is equal to negative 1/4 minus 7 over 4 minus square root 3. Plus square root 3. And this is equal to a negative 2 plus root 3. And yeah, so that would be the problem. Yeah, I do want to say that these problems are all former AMC 10 problems. So if you were wondering what kind of difficulty there were, they're all kind of right here. Again, these are all like technically things that I guess people under 10th grade should already know. So yeah, I'm not entirely sure what everyone is talking about in chat. So yeah, anyway, moving on. All right, so first, I do hope that everyone does follow the solution to the problem that I just did. I thought it's pretty cool problem. So yeah. Next, this one is quite simple. It says how many integers x is this negative? And this is x to the 4th minus 51x squared plus 50. And I guess the key idea here is you have to factor the equation into a product of expressions, because products are easier to work with than sums when it comes to finding their signs, since you only have to deal with the signs of each individual part. So you can kind of treat x squared as its own variable here. Since you have x fourth is just x squared squared, this is just like a quadratic in x squared. And there are a couple ways to factor this. You could, if you really don't know like anything, just right off the bat, you could use a quadratic formula and find the roots and use that to factor. But I think it's actually pretty easy to see that this just factors into x squared minus 50 times x squared minus 1. And again, that's because 50 plus 1 equals to 51, and 50 times 1 equals to 50. So those happen to be the roots of the equation. So we know that this has to be less than 0. So what does this mean? It means that x squared minus 50, x squared minus 1 of them has to be negative, right? So I think it's like kind of easy to tell here that x squared has to be between 1 and 50. Because if x squared is less than or equal to 1, well, for 1, it can't really be, x squared can't really be negative because it's a square. So the smallest it could be is 1. So there's that. And if it's greater than 50, then this is positive. So we know that has to be less than 50 and greater than 1. And it definitely can't be equal to 1 because then it'd be equal to 0. So there are 6 numbers, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and 7 squared within this range, right? And so one might expect the answer to be 6, but you do have to be careful because it says here for how many integers x. It doesn't say for how many positive integers x. So it's multiplied by 2 for all the negative numbers. X can be negative 2 squared, negative 3, all the way to negative 7. And these squares are going to be the same. So there's actually 12 values here that work. So again, this problem, it's really just factoring. And then after that, you really just have to be careful with your negatives. And that's really it. All right. So next we have this. The zeros of the function are x squared minus zeros of this function are integers. What is the sum of possible values of a? So again, you can use abbreviators for this problem. We know that the zeros, we can call them R1 and R2. So we have R1 plus R2 is equal to A, and R1 times R2 is equal to 2 times A, right? And we know that they're integers. So this means that R1 is an integer, R2 is an integer, and A is an integer, R1 times R2 is also an integer, right? So we can just set these equal to each other. So R1 times R2 is equal to 2 times R1 plus 2 times R2. As you can just multiply the first equation by 2 and they're equal. So this looks very familiar. This is exactly just the Simon's favorite factoring trick from earlier. And so if you factor this into R1 minus 2 times R2 minus 2, you get this is equal to 4. And from here, we know that everything's an integer, so it doesn't matter the sign. It could be positive or negative. So again, we can just list out all possible pairs of numbers that these could be, right? So you have like these numbers like this, right? And since R1 minus R2, R2 minus R2, this is symmetric, and we know that A is just going to be their sum. It doesn't really make sense to have 1, 4 and 4, 1 considered. So we can just like eliminate all the duplicate ones. All right, and now R1, now we just consider when they're equal to these values. For equal to 1 and 4, then they're going to be equal to like 3 and 6. For 2 and 2, they're going to be equal to 4 and 4. For negative 2, negative 2, they're going to be 0, 0. And for negative 4, negative 1, they're going to be equal to negative 2 and 1. Right? So these will lead to values of A being 9, 8, 0, and negative 1. And again, these are the only values because everything's an integer. So their sum is just going to be 16, and that's going to be the answer. It's just sum of all possible values of A. So again, this is kind of a neat application of Simon's favorite factoring trick. So yeah, hopefully everyone sees just how this can be useful. Okay, so next, I think kind of wrote over this problem, but I'll just read it. Let A, B, C be 3 distinct one-digit numbers. What is the maximum value of the sum of the roots of the equation x minus A times x minus B, x minus B times x minus C equals 0? And I really just put this on here because it's really a simple problem. And all it really just asks for you is for Vietnamese formulas. And we know that this is going to be a quadratic equation. So the sum of the roots is just the negative of the coefficient of the x term. And we know that the sum of the roots is going to be, for here, it's going to be like negative a, or it's just going to be like negative a plus b here. And from here, this coefficient is going to be negative of b plus c. And we also know that the coefficient of x squared is going to be 2 because we're going to have an x squared from these two and x squared from these two. So like the total sum of the roots of the actual equation is going to be like negative of a plus 2b plus c all over 2. And I do want to mention this negative was actually the coefficient. So when we find the sum of the roots, this negative goes away because we're taking the negative of the coefficient. So we really just want to find the maximum of a plus 2b plus c over 2 when a, b, and c are just distinct one-digit numbers. So I think it's pretty clear that we can just use 8, 7, 8, and 9, where b is equal to 9. So it's just this, and this would be equal to 16 and a half. So yeah, again, this is just a problem where you simply have to know Vietas to be able to do it. And yeah, there's really not much else to it. So yeah. Anyway, I think we actually might be somewhat on time today. So last problem. Says for certain real numbers a, b, and c, the polynomial x cubed plus ax squared plus x plus 10 has 3 distinct roots, and each root is also a root of the polynomial f of x. So what is f of 1? So this ties back to the part where I said that if the roots are the same, then that means that it's divisible. Or okay, so if we let r equal to the root of f4 that's not a root of g of x, of f of x, it's not a root of g of x, so we must have x minus r times g of x is equal to f of x, because everything else has to be the same. All the other roots have to be the same. So then you can simply just multiply it out. And this just becomes like x to the fourth plus ax cubed plus x squared plus 10x. And from the negative r part, this is minus rx cubed minus rx. I'm sorry, not x cubed, x squared. Oh no, it is x cubed. That's my bad. R times a times x squared minus rx and minus 10r. And we know that this has to equal to this. So that means all the coefficients have to be the same. So like, that means c equals to negative 10r. Let's see. I'm actually kind of going out of order here. If we look at the coefficient of the x cubed term, for example, that must mean 1 is equal to a minus r. We also have from x squared term, b is equal to, this is 1 minus a times r. And 100 is equal to the x term, which is equal to 10 minus r. So this means that r equals to negative 90 just from this last equation. And then from here, we can just plug in. So that means a equals to negative 89. And then c equals to 900. And b is equal to 1 minus negative 89 times negative 90. So I'm not quite sure what that is, but we'll just leave that as that. And then f of 1 is simply just the sum of all the coefficients. So f of 1 is equal to 1 plus 1 plus b plus 100 plus c. So this is equal to 102 plus b plus c. And yeah, I don't really, I'm not really gonna like solve like further than this, but I think everyone gets the idea here. You just crunch the numbers basically and add them. And we're out of time here, so that'll be it for this class. Again, the challenge problem is here if you want to do it. And yeah, that's really it. Are there any questions regarding anything that we've done today? I can answer them if anyone asks.